Geodesy lover. So we start with a new session, and before we start talking about the coordinate systems themselves, it's usually good for us to look at the celestial sphere, because there are lots of these elements who we'll be using in our discussion. So first of all, if you remember, the concept of celestial sphere is that the user is located by the center. Oh, I forgot that I have to create these pointer option. So get the option, ink color, the red for contrast. So the observer is at basically the center of the celestial sphere, and you can think in our case as the center of the Earth, and of course is under the effect of gravity, and that defines the line, the vertical line that contains the point, and we have the zenith from one side, the upper portion, and nadir, the lower point. And of course the great circle that contains the the observer and the zenith and nadir is known as the vertical circle. This vertical circle is going to be important, very important for us, as it's used to define certain angular quantities. What we have is there is another great circle that is perpendicular to the vertical circle, which is our horizon, and in this case, in the context of celestial sphere, we call the celestial horizon. And the Earth rotation takes place around the rotation axis that of course is going to intercept the observer, and the upper portion will define the north celestial pole, and the lowest portion that is not visible, the south celestial pole. Now of course this is a situation for it's our situation here in North America. If you go down to the southern hemisphere, it's going to be the opposite. The south celestial pole will be visible, and the north celestial pole will be hidden, and all the stars will basically be circling around the north celestial pole in its apparent movement. The great circle that contains the north and the south celestial poles are known as the astronomical meridian. And now we are going to have a great circle that is perpendicular to the astronomical meridian, and that forms the equator. In this case, that's the celestial equator. So all these quantities are important, and there is another one that is useful, particularly in geodetic astronomy, which is a line of same zenith, of constant zenith, and that's called the Almucantar. And so this line of constant zenith can be seen as if we have an EDM and we just lock the zenith, and if we could circle the telescope of the ADM around 360 degrees, and if we could have a laser beam that could kind of make a mark onto the celestial sphere, that would have a particular Almucantar. Okay, so let's talk about the right ascension system, which I mentioned to you is very important because it defines the CCRS, the conventional celestial reference system, and it's basically give us directions to stars or to celestial bodies, and so we can define that by means of the origin, and you know, the origin has to do with either heliocentric or geocentric, depending on the use of that we're going to give to the system. And the z-axis, this is the primary axis. It's points towards the north celestial pole, and that would be the Z of the right ascension, ZRA, Z of the right ascension. We have the secondary pole. This is the primary pole. This is the primary axis, the secondary pole, and that's the usually called as the x-axis. It points towards gamma. Gamma is the vernal equinox. That's a fixed point on space, and the plane that is formed between the z-axis and the x-axis, we're going to have a so-called equinoctial colure. These would be well, akin to longitude, if you wish, and the y-axis forms this orthogonal system, and if you want to get the position, not the position, direction to a star, what we need is to these two angles, the equatorial coordinates, alpha and delta. That's right ascension, alpha, and delta is the declination. And the right ascension is counted along the celestial equator, which is basically contains the axis x and y, and declination, which is counted along the astronomical meridian of the star. So that would be the meridian that is formed. It of course connects the z-axis and goes all the way to the celestial equator, and it contains the direction of the star. So we are talking here about directions, okay, because it doesn't really make sense to talk about a distance now, because you're talking about very large distances, and everything, if you're observing them, everything you need to know is the direction, so that these elements can be observed. So this is an explanation about the characteristics of the right ascension system, and the origin and the orientation of the axis, and all the elements that relate the Cartesian coordinate with the curvilinear system. So all these definitions follow the basic definition of the elements that are required to define a coordinate system, as we discussed in the first section. So if you want to relate x, y, z coordinates in the right ascension system with the direction, and I like to point out that this is a unit vector. Okay, so it's defining the direction to the star. We can basically, by simple trigonometry, relate the delta and alpha, the right ascension declination, well, the alpha and delta, right ascension declination, and by means of simple trigonometric relations with the x, y, and z. So the x, y, and z, we could think of something like that. So if this is the direction to the star, so basically we have now components x, y, and z, which define the direction of unit vector. Now, star catalogs are based on the right ascension system, and here two examples: the fundamental catalog, FK5, Hipparcos catalog, the two examples. If there is a epoch specified at the star catalogs, we call the mean right ascension system. Okay. Now the word mean in geodesy, mean, it's right, mean, it is the same as convention, because you basically define a, in this case, you define a reference epoch. Okay, and J2000, which corresponds to 1st of January of year 2000, has been used quite heavily as a reference epoch. We're going to see that, well, here it is. The next bullet talks about the International Celestial Reference System, or the Conventional Celestial Reference System. They adopted as the reference epoch 1st January of 2010. So the ICRF2, because there was the first ICRF, was 1st January 2000, and now ICRF2 relates to 2010. Now, this definition of the right ascension system, it is generic, but there are different types of right ascension system. There is the mean right ascension system and the true right ascension system. So the difference basically between these three is that, first of all, between these two mean right ascension systems, we have a reference epoch tau 0. This reference epoch tau 0 is would be the 1st January 2010, as we have today for the International Celestial Reference Reference System 2. Yeah. Well, let me rephrase what I'm saying here. The what is yeah, we have also the issue of a system and frame, okay, in dealing with the celestial frames, celestial coordinate systems. Okay, so the choice of year 2010 has defined the frame. Okay, so I should actually go and get a different color now, because it's getting messier here. And there's someone over here telling me green. Okay, so ICRF, the International Celestial Reference Frame 2, okay, is the one that has the epoch 2010, which means it's dealing with the materialization. Mean right ascension system, at epoch tau 0, reference epoch, mean right ascension epoch tau, and this epoch tau now refer to the date. Okay, this is date, and date for us is not a meeting, but a observation level, epoch of the observations, and the true right ascension system, which is well, I'm going to talk about what difference, basic difference between all these three. Treated geocentric, again emphasizing that the true right ascension system coincides with the system of parent places. Now, what distinguishes, most importantly, what distinguishes all these three coordinate systems are precession and notation. I'm not going to discuss precession notation here, because you already know what it is, but basically the mean right ascension system is a system that is inertial, and referring to a epoch, conventional epoch or mean epoch, that doesn't suffer from precession notation. Okay, now if we allow the coordinate system to suffer from precession, okay, then we have the mean right ascension system at epoch tau. If we have now notation of the coordinate system, we have the so-called true right ascension system. The treatment of precession notation is done by means of rotation matrices, and the rotation matrix matrix for precession is usually in literature referred to as the P matrix for precession, and notation is the M matrix for notation. So I can advance one more slide here. Okay, not too far. Here we are. So the precession matrix is nothing else but a rotation matrix, okay, which is computed by means of 3 precessional elements and or precessional constants, and again it relates the celestial pole that is defined in the reference block 0 to a reference pole at the position block of the date. So and it's done through the precession. Notation matrix, we have the notational elements, and now in this case they have names, the obliquity of the ecliptic, the notation in the obliquity, and notation in latitude, and so they what is going to do in practice is that is going to allow the north celestial pole to notate this, so which means that it's the following notation. Now the elements required for evaluation of P and M are provided by the International Rotation Service, and the evaluation follows expressions defined in International Earth Rotation Service conventions. So the astronomers and geodesists, they get together in these colloquiums, they go around the table drinking tea and eating biscuits, and they define all these things. Okay, so, and I'm going to stop here because it's already lengthy, and the next time we are going to talk about terrestrial systems.